Today we're going to look at the example problems from section 5.5. So in this section we're talking a lot about the side lengths of triangles, particularly how they relate to the angles and also how their measurements have to meet certain requirements. So I'm going to focus in on the first example, and we're going to be writing the angles in order from smallest to largest. And the first thing I'm going to do is highlight each angle its own color. We've got angle F, angle G, and angle H. And what I know about these angles is that their relationship in size is connected to the side that it is opposite. So when I talk about angle H and I talk about the side that it's connected to, I'm talking about the one, if I make an arrow right in the vertex, that it points to. Angle F is connected to this side right here, and angle G is connected to this side right here. Now my little arrows have gotten lost. But what we know is if we can put those segment side lengths in order from least to greatest, then we can easily put the angles in order from least to greatest as well. So my strategy is going to be that I'm going to put those segments, those sides, in order from least to greatest, starting with GH, and then second would be GF or FG, and the third would be FH. And then because I'm able to do that, I can sort of use my color coding that I've set up, and I see that segment GH is yellow, just like angle F, and segment FG is blue, just like angle H, and segment FH is green, just like angle G. And now I've put them in order from smallest to largest. So we've got a similar situation happening in our second example, except that instead of having our side lengths marked, we have our angles marked with a measurement. So I see down here that angle P is 60 degrees, and I see that angle Q is 72 degrees. The one thing that I have to do in order to be able to finish this out is to calculate angle R. And I can do that because I know that all of these angles must add up to 180. So I am going to take 72 plus 60, which is 132, and I am going to take 180 degrees, which would be the sum of all three of my angles, subtract 32, and see that my third angle is 48 degrees. So angle R, if I can write that small, is 48 degrees. So angle R will have the same placement in measurement as this segment. I'm going to connect the order and size of my angles with the side lengths that also represent that same order in measurement. So I've got, in terms of my angles, I've got in order, let's see, angle P is the smallest. Whoops, I made a mistake. I didn't even notice my own angle R. We'll change that to an R. Angle R is the smallest, then angle P, then angle Q. And then to actually match those up with the segments, which is what I'm supposed to put in order, angle R and PQ are the smallest. Angle P and QR are in the middle, and angle Q and PR are the longest, or have the largest measurements, I should say. The next example asks me to tell whether a triangle can have sides with the given lengths. Now, one of the things we learned about the lengths of a triangle is that if I add any two together, they must be greater than, their sum must be greater than the measurement of the third. So I am going to draw my triangle just because that's always my go-to, is to draw what I've got. And I know that it's not accurate, it doesn't really match. But what I want to make sure I'm doing is that I'm adding up the different combos that I need. I need to add up, for example, 7 plus 10. And that needs to be greater than the third side, 19. As a matter of fact, 17 is not greater than 19. So after my first combination of sides, I have proven that no, a triangle cannot have sides that length. And my justification would be that triangle inequality theorem. The next example asks us to do something similar, but it just gives us a little more algebra that we've got to do. I might need to use both sides of my workspace here. So they've given us 3 different side lengths, but they've given them to us as expressions. So I've got side length n plus 6, whoops, side length n plus 6, side length n squared minus 1, and side length 3n, where n equals 4. So they've already told me what to substitute in. I'm going to make this a little larger so I have a little more workspace. And I am going to do a little bit of just sort of pre-algebra work, and I'm going to substitute in a 4 wherever I see an n and do some quick calculating here. So my yellow side is n plus 6, and if I substitute that 4 in the place of n, I see that my yellow side has a length of 10. My green side was n squared minus 1, which means I'm going to take 4, square it, and then subtract 1. That is 16 minus 1 is 15. And then my third side is 3n. I'm going to replace my n with a 5, or excuse me, with a 4. And my side length is 12. So now I've got to do a little testing on those. I've got to say, if I add any of those two together, are they greater than the third side, which they need to be? So if I move over a little bit, and actually my measurements come with me, that's okay. I'm going to do a little bit of color-coded adding. So the first thing I need to do is add my yellow and my green. If I add 10, my first side, plus 15, my answer should be greater than 12, and it is. Now if I add my 10 to my blue side, which is 12, that solution should be greater than 15. My green side, which it is. Now the last combination I need to do is I need to add my green 15 to my blue 12, and that solution should be greater than 10, and it is. So the solution to this is yes, a triangle can have those measurements. And all of my evidence is in my algebra proving that if I add two sides, their sum is greater than the third side. Now my last example talks about a triangle that isn't here, so I'm going to draw it. The lengths of two sides of a triangle are 8 and 13. Find the range of possible side lengths for the third side. So I'm going to label this triangle 8 and 13. I just like to visualize what I'm doing. And what I know is that this side here has to meet a couple qualifications. I'm going to do my highlighting again, and I'm going to give 8 the color yellow, 13 the color green, and my unknown the color blue. So if I move this diagram over, what I know is that whatever my question mark is, if I add, whatever my question mark length is, I should say, if I add it to, if I add my unknown, we'll call it x, I suppose. If I add x to my yellow 8, that solution has to be greater than 13. So what I can do is solve a little mini equation and realize that in that case, x would have to be greater than 5. I also need to show that if that unknown x were added to the green 13, that solution would have to be greater than my yellow 8. Now in this case, when I solve, if I subtract 13 from each side, I find that x would have to be greater than negative 5. This one almost doesn't count. I'm going to actually put a little highlighted rectangle around it. It doesn't count because there can't be a measurement that is negative. Now my third example is going to be adding up my yellow and my green. My yellow 8 added to my green 13 have to be greater than that unknown side x. And so if I add those two up, that means that x has to be less than 21, or 21 has to be greater than x. So there's a range of solutions that would work for this. And what I'm going to do is I'm going to take this inequality where x has to be bigger than 5, and this inequality where x has to be smaller than 21, and I'm going to write it as a compound inequality. So I put my x in the middle, and I declare that x has to be smaller than 21 in order to be a part of this triangle, but x also has to be larger than 5 to be a part of this triangle. If it meets that qualification, then I know that this is a triangle according to the triangle inequality theorem.